So we pretty well covered all the material I wanted to cover in this chapter, and we just need to solve problems, solve problems, solve problems. There's something very abstract, something very difficult to understand. It's at the end of the chapter, but it's the lead-in. It's the lead-in to the next chapter, which deals with entropy. Entropy is a new thermodynamic property, and it helps us quantify the second law of thermodynamics. And so Clausius, this person, came up with that entropy concept based on his inequality that we study. And this is my best shot at trying to get you to understand maybe why entropy comes about. Because if somebody says, talk about energy, you can do a pretty good job. Temperature, you can do a pretty good job. Pressure, you can do a pretty good job of talking about those. Entropy, even after you pass this class, you'll be hard pressed. I don't know, it's a property. What's it defined as? Well, it's hard. But it's going to come out of this Clausius inequality. So what's the inequality? It says that the sum of the heat transfer into the system, if it's negative, then it's out of the system, divided by the boundary temperature for the entire cycle is equal to less than or equal to 0. So they make it an equality by making it equal to something that's negative, and this is the strength of that inequality. And as it gets greater than 0, you get more and more irreversibilities. So if I said its value is 0.2 versus 2 versus 20, well, this is more irreversible and less. And if it gets close to 0, then it's reversible. What happens if that is negative? Well, you broke the second law of thermodynamics. It's impossible. Let's solve a problem. A reversible power cycle with 40% thermal efficiency receives 50 kilojoules by heat transfer from a hot reservoir at 600 Kelvin. Let's organize that information. So we have I call it a heat engine because it's operating a power cycle. The purpose is to produce some work by bringing in some QH from some high temperature reservoir. The high temperature reservoir is 600 Kelvin, and it receives 50 kilojoules of heat from that 600 Kelvin high temperature reservoir, and the thermal efficiency is 40%. And it's a reversible power cycle, so rev heat engine. All right. The cycle rejects heat by heat transfer to a cold thermal reservoir, so we put down here TC, and we're rejecting heat QC. Determine the heat transfer to the cold reservoir, so find QC. And for part B, the cold reservoir temperature, TC. All right, so I'm looking for TC and I'm looking for QC. Did they give me W? No, it's not in the problem statement. Not in the problem statement. Well, there's a couple things that we would try to bring to bear. One of them, what is the definition of efficiency? The thermal efficiency. So the thermal efficiency equal to what we desire over what is supplied from the hot reservoir. All right. If it's a reversible power cycle, is that thermal efficiency equal to 1 minus Tc over Th? It is. You could use that. There's more than one way to solve this problem. You could use that information to solve for the answer for part B right away, couldn't you? Let's go ahead and solve for part B right away. So Tc is equal to 1 minus the efficiency times Th. Because it's a reversible power cycle, that gives us the maximum thermal efficiency, 1 minus Tc over Th. And we can calculate that the temperature is 360 Kelvin. How do I find the heat transfer to the cold reservoir? Well, I could think about using the first law. for a control volume around the heat engine, or that's the system, the heat engine. It has heat transfer in, heat transfer out, work out. And from the first law, we find that H is equal to W plus QC. Is that true? And then also we can replace that W by eta times QH. And so QC is 1 minus eta times QH. So QC is 1 minus, so 60% of 50 kilojoules. 60% of 50 kilojoules, 30 kilojoules. So just as an aside, the work is 20 kilojoules, isn't it? The work is 20 kilojoules. Here's a clicker question. So if the thermal efficiency goes down, let's say it goes down, so from here, from 40% to maybe something like 38%. So the thermal efficiency, I'm asking you, it goes down. It goes down, okay? That's the premise of the question. What happens to QC? Does QC go up, stay the same, or go down? If you think it goes up, answer A. If you think it stays the same, answer B. If you think it goes down, answer C. I just turned it on now so you can input your answers. The efficiency was 40%. There's now some irreversibilities. It goes down. What happens to QC? So the purpose of a heat engine is to take as much of this QH and convert it into work as possible. True? But some fraction of it has to be dumped to the atmosphere. Think about thermal pollution. Thermal pollution, right? You just have to get rid of it. You don't want it, but you have to dump it to the atmosphere, all right? The best heat engine will convert most of QH to W. The reversible heat engine is the best. If you start to have some irreversibilities without changing the temperature, TH or TC, which we don't change, nothing in there saying we're going to change that, the two temperatures, the hot and the cold thermal reservoirs. But if the system's performance degrades due to irreversibilities, the presence of irreversibilities, more waste heat has to be dumped to the atmosphere. QC has to go up. Work will go down. So if you wanted to think about numbers, you say, well, I had 50 come in. I used to have 20 go out here. Maybe this 20 changes to 18 or something like that. Instead of 20 kilojoules, maybe it goes down to 18 kilojoules. And you used to have 30 kilojoules of heat go out. Maybe it has to be 32 to go out. Make sense? Let's go ahead and grade it. So what happens is the amount of heat has to be rejected goes up. Another problem. A power cycle receives 750 kilojoules by heat transfer at a temperature of 1500 Kelvin and rejects 100 kilojoules by heat transfer at a temperature of 500 Kelvin. And another heat transfer from the system occurs at a temperature of 1000 Kelvin. So I have to have a system with 3 heat transfers. So I'll say Q1 coming in at TB1 and Q2 going out at TB2 and Q3 going out at TB3. So 1 in and 2 outs. The 1 in is 750 kilojoules at a temperature of 1500 Kelvin. The second temperature, or the second heat transfer, it's going out, so it's 100 kilojoules. Professor, how come we don't put a negative 100? The direction supersedes, right? And so we've been talking about a positive QC out of the system to the low temperature or cold reservoir, right? Okay. And then this is the TB2, which is 500 Kelvin. And then Q3 we don't know, but it happens at 1,000 Kelvin. This is a power cycle. There's one more energy transfer. We need W. W out. If the cycle, and then they give this, sigma of the cycle is 0.05 kilojoules per Kelvin. What is that? That's the strength of the inequality in Clausius's inequality. We're going to learn about entropy next chapter, and that will be linked to entropy production. We don't like a lot of entropy production, especially when trying to maximize the power production out of a heat engine or a power cycle. Anyway, calculate the thermal efficiency. So we want to calculate the thermal efficiency. What would it be? What's the definition of thermal efficiency for this problem? Clicker question, huh? Should it be W over Q1, or should it be W over Q2 plus Q3, or will it be W over Q1 minus Q2 minus Q3? Clicker answer A, B, or C. And you only have 30 seconds, no extensions. What is the thermal efficiency? Or do I need to give you more time? You have enough time? All right. The same is true for thermal efficiency as for coefficients of performance. Thermal efficiency of power cycle or heat engine, coefficient of performance for refrigeration system, coefficient of performance for heat pump system. All of these have a simple ratio. It's what you desire over what you have to pay for. What it costs. Desire over cost. All right. What do you want out of a heat engine? Work. That's good. All three answers had the work in there. But what did you have to pay for? Q in from the high source, high temperature source. You have to typically burn a fuel. You say, well, isn't it thermal pollution? Yeah, the EPA is going to tax thermal pollution, but not now. Okay, it's coming. You know, all things will be taxed. That'll be a cost. Anyway, so what works the best for this one? Isn't answer A the best? Yeah, that's the best. All right. So now let's get rid of this. Okay. Now I need to find the work, don't I? I'd like to find the work directly. If I write the first law, what I'll find is the work out is equal to Q1 in minus Q2 minus Q3. That's the first law. Analysis, conservation of energy. But I don't know Q3. So how am I going to solve for Q3? Well, this is the hint right here. This red line is they gave us the strength of that inequality. Let's use Clausius's inequality. So if you use Clausius inequality, turned into an equality with that constant, then what we have is we have Q1 over TB1 in minus Q2 over TB2. Why the minus sign? Because it's an out. And I want to talk about a positive Q2 minus a positive Q3 out of the system divided by TB3. And the sum of everything on that side is equal to minus sigma of the cycle. True or false? Is that true? Look good, huh? So the only thing we don't know in this equation is Q3. Let me just put the numbers in. 750 divided by 1500. That'll be kilojoules per Kelvin minus 100 kilojoules divided by 500 Kelvin minus Q3 unknown amount in kilojoules divided by 1000 Kelvin equal to a minus 0.05 kilojoules per Kelvin. And when you solve for Q3 from that energy balance, the Clausius statement, you find Q3 is equal to 350 kilojoules. Now you can come up here and you have the work is going to be 750 in minus 100 out minus 350 out. So the work is going to be 300 kilojoules out. Then we come up here to thermal efficiency is 300 divided by 750, and the thermal efficiency is computed to be 40%. Even though I have, 3 heat transfers, I have a high in with 2 outs at different temperatures. All right? That makes sense? Okay, let's continue on. A refrigeration cycle operating between 2 thermal reservoirs. TC is given, TH is given. Let me make a sketch right here. It's a cycle. This is a refrigeration cycle. You have, I'll draw it as a hot TH of 315 Kelvin and TC of 300 Kelvin. Since it's a refrigeration, we want to draw QC not going to the low temperature, but going from the low temperature to the system. And then we have to reject heat, QH, to the high temperature, and we have to supply work to the cycle. Isn't that the refrigeration? So our directions have switched from the power. They tell us that the coefficient of performance for the refrigeration cycle is a value of 6. Okay? From the information given, does the cycle operate reversibly, irreversibly, or is the cycle not possible because it violates one of the laws of thermodynamics? I'm going to throw that open. I'll let you work on this for a couple, let's say, how long? A minute and a half? 2 minutes? 2 minutes. All right? And then you'll collect A, B, or C. So there's a little over 2 minutes. Go ahead. All right, so somebody said, is the coefficient of performance refrigeration cycle the maximum? Is that 1 minus TC over TH? Is that true? Reversible heat engine. How about a reversible refrigeration cycle? Oh, that's this one. It's equal to TC over TH minus TC. How many people were looking for that equation and found it? Yeah, right? So what you want to do is when you stick in your numbers, you find that, it's going to be 300 divided by 15, which comes in at a whopping number of 20. So the maximum coefficient of performance for a reversible refrigeration cycle operating between a high temperature reservoir at 315 and a low temperature reservoir of 300. 315 and 300, right? I may have misspoke on my temperature, sorry. Then is 20, right? Meaning if I wanted to pull out 1 kilojoule here, if I wanted to pull out, make the math easy, 20 kilojoules of heat, how much work would I have to supply? 1 kilojoule of work. How much would I have to dump? 21 kilojoules. That's how you use the coefficient of performance. Isn't the coefficient of performance refrigeration what I desire? What do I desire out of a refrigeration system? Cooling. I want to cool. I want to cool things down. Divided by what it costs. That's what I have to supply. So if that number is 20, then if I supply a work of 1, I could remove a QL of 20, meaning I have to throw away to a QH, or Q, I switch between L and C, sorry about that, but you have to throw away 21 kilojoules. Does this all make sense? But now they say, for this problem, the coefficient of performance is not 20, it's 6. So what's the best answer? Well, I'll tell you what, I'll ask another clicker question, and then, but you only have 30 seconds on this one. Same question, you've gotten more information, A, B, or C. So there were some Carnot corollaries. They said that the coefficient of performance, refrigeration, compare that to the coefficient of performance refrigeration maximum as if there's no irreversibilities, right? They said if this is less, then you have some irreversibilities present. If the coefficient of performance observed is equal to the coefficient of performance maximum theoretically possible, it is reversible. And if the coefficient of performance reported in your design or observed is greater than the coefficient of performance refrigeration maximum, then look for some error because it's not possible. It violates the second law. True? All right, let's go ahead and grade them. So, it's some irreversibilities, isn't it? That's why the COP is less. It's 6 instead of 20. And so there you go. That's question 3. We already graded question 2. So we went from a class that's 62% correct to a class that's 72% correct, leaving still 18% questioning why. So if somebody came in and they said, no, my reported COP is 25, what do you say? It's not possible. It violates a law of thermodynamics, and basically it violates the second law because you have coefficient of performances here. All right, this problem will take the rest of the time. Ready to get started on it? So water executes a Carnot power cycle. When you see this word Carnot, what do you think? Maximally efficient, no irreversibilities. Everything is reversible. And the Carnot power cycle would be broken into 4 processes or 4 components. Either way, let's read the rest of the problem. The Carnot power cycle by steadily circulating water between 4 components: a steam turbine, the condenser, the pump, and the boiler. So if you have turbine, here, do it this way. We'll put the boiler, we'll put the turbine, we'll put the condenser, and we'll put the pump. And the fluid flows out of the boiler into the turbine, out of the turbine into the condenser, out of the condenser into the pump, and out of the pump into the boiler. Now, it's been common to go ahead and label these states 1, 2, 3, in 4. Okay, the turbine and the pump are well insulated. Maybe you put some hash mark like this. The turbine and the pump are well insulated. So Q dot is 0 for both of those components. The condenser and the boiler operate at constant pressure. That means P1 is equal to P4 and P2 is equal to P3. There's no pressure drop through the boiler or through the condenser. Changes in kinetic potential energy are negligible. Property values are given in the table. So they said state 1, 2, 3, 4. State 1, look at the pressure compared to state 2, compared to 3, compared to 4. So pressure at 1 is equal to pressure at 4. Is that in agreement with the table? Is the pressure at 2 equal to pressure at 3? Is that in agreement with the table? Which is low pressure? The boiler? No, that's high pressure. What's low pressure? The condenser. Okay. What about the temperature? 250, 250. So this is T1 and T4 have the same temperature, but you're adding heat. How did that happen? How do you have heat added and yet the temperature doesn't go up? Phase change, going from liquid to saturated vapor. And what about the condenser? Are you going to have heat transfer out of the working fluid in the condenser? And it's happening at constant pressure and the temperature's the same. What happened? Same thing, phase change. You're condensing some. Now, you don't condense all the way from saturated vapor to saturated liquid. You condense from about 75% vapor down to 28% vapor. See what you're doing? You're condensing part of the way. You have the specific volume is given, you have the internal energy is given, and you have the enthalpy given. They're just magically given. You asked me a question earlier. Well, some of these problems take so long to work. How do you shorten it up on exam? You give them a table of half the properties and say, only go and get the properties you need. Or use the properties that are already given you to answer the questions. Problems at the end of this chapter, sometimes you got to go get all the properties. Plus, you got to make the calculations, etc. So that's how you make an exam question to be more doable in the time limit that you have. Okay. So let's read the problem. Part A, sketch the cycle on a PV diagram. I want you to sketch it. I'll walk around and see how far you get. I want you to sketch it on a PV diagram. All right, so we want to put it on a diagram. I'm going to try and tuck the diagram in here, but you really need room to space out that diagram. What's on the x-axis? V. What's on the y-axis? P. All right. I'm going to put a dome, and the dome is going to be extremely steep up to this point, and then it's going to really kick out. Really, really, really kick out. And we have a high pressure up here. That high pressure's 3,976 kilopascal. And so it starts at state 1. It's saturated vapor. True. So let's put state 1 right there. And then we undergo an expansion to a low pressure of 19. So I know this is right here, what did I say? 3,976. Right here is 19.9 pressure, kilopascal. And you're at some quality, maybe this is 75% quality, right there, state 2. So you went from 1 to 2. Okay? Then you go back to 3. 3, you're going to be maybe right here, state 3. And then from 3 up to 4. And then 4 over. Now, some people, I didn't do this even as well as it should be because the largest specific volume is 5.7, right? And then the next one is state 3 at 2.1. And then at 1, is 0.05. I didn't make 3 much larger than 1. It needs to be even more over.
It's not to scale.
It's not to scale at all, right? But I'm trying to show you what it looks like, okay? And then for 4, it's 0.00125. I mean, it's really small. True? All right, so there it is. I tried to do a little better job of showing on a PV diagram. Next part B, evaluate the heat transfer and the work for each component. How many components? Boiler, turbine, condenser, pump. 4. Q and W for each of them. I have to have 8 things to calculate, true? So I'll put it in this table. The component, turbine, condenser, pump, boiler. In that table, 2 of them are really easy. The Q's for the turbine and the pump, they are well insulated. There's no heat transfer per unit mass flow through them. But now let's analyze the turbine and let's introduce a control volume around that turbine. We know that the work traditional is out of the turbine. That's a lowercase WT. Okay. The rate of change of energy in the control volume with respect to time is equal to the rate at which it's flowing in with heat minus it goes across the boundary in the shaft power out, plus it flows in with mass, bringing with it its enthalpy, neglect changes kinetic potential energy, minus going out the enthalpy. So it's operating steady state. I divide everything by the mass flow rate. It's also, I should have necked that one, it's well insulated. So I get lowercase w out of the control volume for the turbine is equal to H1 minus H2. It comes in with high enthalpy, it goes out with low enthalpy. The enthalpy difference equals the work per unit mass out. I look in the table, 2801 minus 1997.2 gives me 803.8 kilojoules per kilogram work positive out. Let's do the pump right away because it's a very similar equation. Now, you can do it where you put the work of the pump positive out. I'll do it that way. The work of the pump positive out. You're not going to get a positive work out. It's a change in the enthalpy, H3 minus H4, which comes in at negative 180.8. Why do I want a negative for the work of the pump? Because when I do the sum for that column, I'm going to have a plus there and a minus there, okay? All right, let's continue on. What about the condenser? Is there any shaft work being provided out of the condenser? Does the condenser have something like W dot coming out of it? 0. And what about the boiler? You do the first law for the condenser. And what we find, let me just write it down. The rate of change of, the rate of change of energy in the control volume around the condenser with respect to time is equal to the Q dot into the working fluid minus any shaft work, none, plus the mass flow rate coming in at 2 minus out at 3. So it's steady state, no shaft work. So we find that lowercase q is equal to H3 minus H2. The enthalpy at 3 is a lot lower, 904.9, subtract off, and we find that for the condenser, it's negative 1092.3. Why is it negative? It's heat transfer out of the condenser, not into the condenser. I need to hurry up a little bit, do the same thing for the boiler. The boiler has 1715.3 kilojoules of heat into the boiler. When you do the net, 623 and 623, are these the same? Yes, and if they're not the same, look for your error. Okay, now we have all of the component heat and work transfers, everything per kilogram of steam going through the system. Now evaluate the cycle thermal efficiency. The cycle thermal efficiency is what you want. What do you want out of the power cycle? A large net positive workout. So that's going to be 623 kilojoules per kilogram over what you had to put in, what you had to pay for to make it run. What do you have to supply? The 15.3, absolutely correct, in the boiler. And so you calculate the thermal efficiency to be 36.3%. Somebody says, is this a Carnot vapor power cycle or a Carnot power cycle? It is. Somebody says all the heat's brought in at 250 degrees C. All the heat's rejected at 60 degrees C. Can I use 1 minus Tc over Th? If I put 1 minus, the low temperature is 60 divided by the high temperature 250, will I get 36.3%? No. Why will I not get it? Because I absolutely must be an absolute temperature scale. And it's degrees C. So I fix it by adding 273 and adding 273. I'm sorry? The temperatures have to be in Kelvin. This temperature is degrees C. I'm sorry. I didn't correct that fix. If you look up the value, you'll see the saturation pressure at 250 C. And now you'll get 36.3% thermal efficiency. It'll be an agreement, okay? Thank you for your attention. See you Wednesday.